The next part is mine, last but not least, an outlook on CAN-based networking. What is state of the art, what we are working on, and how this may apply also to lift applications. Almost currently we have, not really have, we currently have 2 generations of CAN, and we are working on the 3rd generation of CAN already. CANopen Lift was designed or is designed with the use of classical CAN, with the use of CANopen as we know it. That said, and I started already today with that, we have some limitations in classical CAN. Today we are running at 250 kilobits per second. We have payloads up to 8 byte. A 2nd generation of CAN was developed a few years ago for that reason, called CANFD. That is available today in hardware. It provides higher speeds. Even with the same arbitration speed of 250K, we can run at data speeds of 2 megabits or even more. And we have payload sizes up to 64 bytes. The next generation we are working on is called CANXL. It's still under heavy development, I must emphasize on that. It is intended to run at 500 kilobits per second and with data rates up to 10 megabits per second, and the payloads could be up to 2 kilobytes. Yeah, classical CAN has some limitations, and for general control purposes, it's quite good, but we have limitations, especially if we think about software updates, if we think about, especially maybe in lift applications, if we want to make emergency call, voice calls, I must emphasize, maybe even video calls, things you can't really do with CAN these days. So there are still limitations, and how can we overcome this? As always, automotive were the first. Automotive were the first in developing CAN, and we use it in many applications these times. So automotive was also the one who give pressure on further development of CAN into what we have today as CANFD. The requirements is higher bandwidth for software download and for diagnosis, higher bandwidth for calibration and universal measurement purposes, and higher throughput for automated driving, or at least go into a way of automated driving, and of course for functional safety and cybersecurity purposes. That said, we as CANopen Automation are not speaking only for automotive. So we try to put in and to give a voice also to other industries. And that we tried first with CANFD as well. We tried to give emphasis, a voice for the requirements of other industries. Of course, here again, higher throughput for motion control applications, maybe even larger payload for motion control applications. Because in motion control applications, especially where I have more drives like X, Y, Z controls, with classical CAN, I have a synchronization problem. I have to send commands once after another and have then to synchronize on something. With higher payloads, I can transmit for all drives the commands within a single message, so I don't need any specific synchronization because the reception of the message is the synchronization trigger. The same in general for data acquisition. We need larger payloads for safety and security, software download, diagnostic. And what's also is we have already huge investments in terms of education and things like that. And in many industries, we don't want to implement new systems because that would require new investments, additional investments for education. It's easier to build up from existing knowledge. Of course, the physical layer must be requires the same robustness as we have with classical CAN. The idea of CAN-FD is as simple. In classical CAN, we have a message. We can subdivide the transmission of the message in the arbitration phase, in the data phase, and in the acknowledge phase. In the arbitration phase, we are trying to find the device, the controller, who is now allowed to speak up, who is now allowed to transmit its data. That's been identified by the priority in the identifier. Then when the one device with the highest priority message is being found, it transmits its data, and afterwards we acknowledge it. The same applies for CAN-FD. We have the arbitration phase, the data transmission phase, and the acknowledge phase. And the idea behind CAN-FD is while we have found the single most important message, we are now almost alone on the network, on the bus, because we want to transmit our data. And if we are alone on the bus, then we can speak at any speed. We are not limited. And so that is the idea behind CAN-FD, flexible data rate. In a flexible way, we change the transmission rate during transmission to a higher speed. Up to 50 megabits has been shown in the lab at that time. Practically today we have available without specific requirements 2 megabits. And maybe up to 5 megabits practically with some special transceivers. So that's the general idea behind FD. We have longer payloads available, up to 64 bytes. And the same arbitration field with 11-bit or 29-bit identifier, and some additional control fields, additional CRC, larger CRC, because we want the same robustness like classical CAN. We want to be able to detect errors and learn. I have some graphics, some curves on the efficiency. In this example, we are trying to transmit a CAN message with an 8-byte length. On the we see that we try to transmit it at 500 kilobits. Even the data phase is at 500 kilobits. Of course, then we have an average bit rate of 500 kilobits. If we increase the data rate up to 1 megabit per second, we already have roughly, I don't know, maybe the average bit rate of 0.8 megabit per second. If we increase just the data rate, we are still talking about an arbitration rate of 500 kilobit. We are still talking about the same message with 8 bytes of data. And if I just increase the data rate in the data phase to 2 megabits, we have already an average bit rate of, I don't know, 1.2 megabits per second. So that's already more than we have today with classical CAN. And we can run network lengths like today with the limitations of a 500 kilobit. That would translate to 100 meters. If we increase the data rate up to 4 megabits, we are almost, I don't know, up to 1.4 megabits per second at an average bit rate. Comparable curve, we now having fixed bit rates of 500 kilobit per second in the arbitration phase and 4 megabit at the data phase. And with a payload size of 8 byte, we are at the 1.4 average bit rate, 1.4 megabits per second. If we increase it to 16 bytes, so twice as large, we are almost, I don't know, 1.8, almost 1.9 megabits per second. If we double that again to 32 bytes, we are already almost 2.5 megabits per second. And if we use the full message length of 64 bytes, we are almost 3 megabits per second. So we can have a huge improvement. The network length limitation applies to the arbitration speed to 500K. We are still talking about a network length of about 100 meters. And the improvements are even higher if, like for lift applications, we could use the arbitration speed of 250K and still have use also the data phase of 4 megabit, and then we have a much higher improvement. So that means we have higher data throughput that reduces latency, that could increase accuracy for the drive. So we could have, with CANFD, we can have a high, better control, better networks. CANFD is nothing from the future. CANFD is available today. The controllers, the transceivers, hardware on different levels, and it is even available in a system. Volkswagen, all the cars are sold these days by Volkswagen, or the new all-electric. The ID.3 has CANFD inside. Also, the Golf 8 has CANFD inside. I just drove the Golf 8 last week when I had a rental and was going to a conference. So yes, it is available and it works. I said it's no problem to run it with 2 megabit per second in the data phase. It can become a problem using higher bit rates. At Canon Automation, we try to give system designers more to the hand and provide implementation recommendations. So we have for that our 601 series. And I want to emphasize here on part 4 on the signal improvement circuitry, which is very important for the higher data rates. What's the problem of the higher data rates? The problem is when we switch states from recessive to dominant, then we get something what it's called ringing. We have an overshoot and then it comes back and it's a short ring. That's something with lower speeds, that's not a problem. But if we shorten the bit time, then we need to sample at some point. And at some point, we are going into the places where the ringing takes place. It's not so much a problem in the switch from recessive to dominant, but while it's a switch from dominant to recessive. Because recessive to dominant is actively driven. So it's not much of a problem. But switching in the bits from dominant to recessive, that's not actively driven. That's left open. So we have a much undershoot and back. And if we sample at the wrong point, we may sample the wrong bit. And so signal improvement means that a transceiver dynamically changes the network impedance into the way how we want to have it to compensate for this kind of ringing. I said CANFD is available in hardware. We also worked hard on to make CANopen usable with CANFD. We published it as CANopen FD, CIA 1300 series, specifically 1301. We made all the use of all the possibility of CANFD, especially the PDOs, now available for up to 64 bytes. And we introduced a new service called USDO, Universal SDO, to replace the existing SDO. And the advantage is not only that the Universal SDO is not only now having larger payloads, there is also another very important part, bit why USDO is better than SDO. With SDO, we always had in a predefined connection set only a setup of an SDO connection between one manager and multiple clients. But with a USDO, we now are able of a fully meshed communication. So any device, any CANopen device can talk to any other device without any required setup. We don't need additional setup. That is now available with the existing default communication set. It allows us also a security option and of course the higher bit rates. And we also improve the layer setting services to use of this. So CANFD is available. CANopen FD is available and ready to use. That's state of the art. I want to give you also a short glimpse on what is the next what we are working on. It's called CANXL. CANXL is also heavily driven right now by the automotive industry. It's still under development. We have no fixed specification right now. We hope that we can fix it till the end of the year. So you see, we have another 4 years, maybe 5 years ahead before hardware becomes available. What's the requirements? What's the features of CANXL? The features is it will be backwards compatible to CANFD. We will have no compatibility issues. That means if I have today an existing CANFD network and I put in 2 CANXL nodes, they can communicate on the same network and we will have no interference whatsoever. CANXL will also have the 11-bit CAN identifier as a priority ID. We have the payload for up to 200 kilobytes of data. And we have an additional 32-bit address field. Today, we are mangling the address somehow into the CAN identifier together with a priority. In CANXL, we have a dedicated 32-bit address field. We also have a virtual CAN ID. We have additional CRCs because we want the same robustness what we have with classical CAN and with CANFD. Maybe it's being better. I said already we have a difference between now priority and address. We can differentiate between those two because we have the 11-bit CAN identifier plus additional 32-bit address field. We will have a virtual CAN ID in addition. It's an 8-bit field. So we can distinguish different virtual networks on the same cable. That makes CANXL useful also for backbone communication. So that means what I have today, maybe with my physical CAN cables, I can nowadays combine them onto the same cable. And we introduce also an additional identifier, the so-called service data unit type. This will indicate the protocol used in the CANXL message. That could be either a legacy CAN-based higher layer protocol. That could be tunneling of Ethernet frames. We are defining currently right now, or we are producing the specification on how to tunnel Ethernet frames and identifying them. Of course, classical CAN-FD frame. We can also do TCP/IP segments, and on the future topic list, not being done right now, is how to channel CANopen FD, J9039, or maybe other protocols as well. What we are also defining into CANXL directly, into the hardware, is a security option. So that means we can, the hardware controller can transparently authenticate a CAN message and can identify if it's authentic or not. And we can also not only validate authenticity, but we can also encrypt the data. And all this is transparently done by the hardware. We are working also on that specification right now. Yeah, that should be a short outlook on CAN-based networking. With CAN-FD available today, which can be used today, we have already huge improvements for existing applications. And with CANXL ahead in the next 4 or 5 years, maybe 6 years, I don't know. We will have a future outlook, and we can have higher data rates. We can tunnel dedicated networks through. So like if I have an internet access gateway, I can from the outside tunnel through to my specific device to make a service, software download. I have security options, all these kind of things. So I will have a future with CAN-based networks. Okay, thank you for listening. Thank you for your time. That should be for the CAN Tech Day. I thank also all the speakers